Hello and welcome everyone. Today I'm going to talk about front-running protection for smart contracts. So let's share my screen. Okay, so thank you to Ermias and Anthony for their comments. They've helped with me put this talk together. So there are three main types of protocols. You've got multiply sign, where you're assuming that you trust a group of actors. You've got optimistic, where some information is expected to be true unless it's proven otherwise. And ZK, which I guess is the opposite of optimistic, where you know something is true because you post a proof. So optimistic protocols have watches, and they observe the protocol participants and submit fraud proofs to contracts if they see something bad happening. And the first watcher to submit the proof gets the reward. However, if you don't design your contract carefully, MEV bots can observe what's going on and front run you. So they can submit a transaction ahead of you based on your transaction and get the reward instead of the actual watcher. So I'm going to talk through some ideas I've got on how you might try and write a contract so that it minimizes the risk of being front run. And so I'm going to work through this agenda. So in optimistic rollups, you have users who submit transactions to operators. Operators put together a batch of transactions. They submit the compressed transactions and the state root to a contract on the chain being rolled up to. Watchers observe what's going on, and if they detect the invalid state root, then they will submit a fraud proof to show that that shouldn't be there. For bridges, so bridging between two chains, you can have optimistic bridges. And in this scenario, a user submits a transaction on the source chain, some message is generated, so some event, and a tester observes those events and creates a Merkle tree of events. And in fact, they create an incremental Merkle tree, and they will sign the root of the Merkle tree. Then relayers will submit the signed root to the destination chain. After the fraud proof window, the user can then submit their transaction. So if an attacker takes over an attester, say powerfully owns them, or if an attester is acting maliciously, then they might have a create a Merkle root, which is based on a transaction that wasn't on the source chain. And they could submit that signed Merkle root to the destination chain. And then watchers will see this and say, hey, that's fraud. And they'll submit the malicious Merkle root and a fraud proof on the source chain to collect a bounty. And the other attesters will work together to multiply sign something saying, hey, that Merkle root is malicious, it should be discarded. And then the attacker will hope that that doesn't happen quickly enough, and they can submit their malicious message based on the malicious Merkle proof and Merkle root. So when we think about these optimistic protocols, there are three main properties. You want the fraud proof submission to be as quick as possible. You want everyone to know, you want people to be slashed as quickly as possible to prevent further fraud. You want as many watches as possible so you can't bribe them, because if you've got, say, 1,000 watches, it's harder to bribe 1,000 watches than, say, only 10. And especially if it's permissionless, you don't even know who all of the watches are to bribe. And so the watchers have to be incentivized and compensated, to do the work that they're doing. So rather than trying to work through, say, an optimistic roll-up or an optimistic bridge, I'm going to come up with a more simplified version of this problem. So assume that anyone can receive a 1 ETH bounty if they submit a proof. And the proof is that a number is divisible by 13. So say if you have 26 mod 13 is 0, so it's divisible. But the bounty is only paid to the first person to submit the proof. So you could get a proof for 26, but you couldn't get another one for 26, but you could for 39. So as long as you're the first one for that particular number. And so whoever submits the proof first gets that 1 ETH bounty. So a simple code that would do this is this contract here. And so, you require that the fraud proof hasn't been submitted yet and revert otherwise. You require that it's a valid proof so that the number really is mod 13. And then if it is, then you update that thing saying that, yes, this proof's been submitted. And then you pay the 1 ETH to the message sender. And you blow up if for some reason or other the 1 ETH can't be sent. So the transaction that is, that submitting to that function is this. So this is the call data. And so you've got the actual function selector, which is, the kick of submit proof uint256. And then you've got that parameter, which was the proof, and that's 26, which is 1A hex. So let's think about front running and how does it actually happen? So we've got that transaction, which was, going to submit that fraud proof with the number 26. And so a user submits it into the transaction pool. And then the first thing that happens is it's gossiped via the peer-to-peer network to other Ethereum clients so that all of the possible miners will know about that transaction to maximize its probability of being included in a block. And then one of the clients will, put it into a block and then use the consensus protocol to say, look, here it is, this is the valid block, and then gossip the consensus across the network. So obviously now that we're in the era of beacon chain and execution chain, that consensus is separated, but it still holds. So when that transaction is in that transaction pool and being gossiped around the network, an attacker, a front runner, could see that transaction and they could say, hey, look, if I submit that transaction, I'll get the fraud, the bounty, I'll get the bounty. So they'll then submit that transaction, let's say offering a higher tip, a higher gas price. And so they'll have their transaction accepted. And then when the user's transaction goes through, it'll hit that require, which says that the proof hasn't been previously submitted and their transaction will revert. So you can have, or there are general purpose front running bots. And so they determine what to front run by doing trial executions of all of the transactions in the transaction pool. And they set themselves up as the signer of the transaction, so the message sender. They replace they scan the call data for addresses, and any address they see that is the message sender, they then replace with their own address. And so they also look for internal cross-contract calls that might get called as well. And when they're doing these trial executions, the question they're asking themselves is, do I end up with more assets? So do I end up with more ETH or ERC20 tokens or ERC721 tokens as a result of doing this? And if they do, then it's worthwhile front running. So, and so when you've got a contract, they're aiming to call submit proof ahead of the other contracts, other users. So MEV, minor extracted value or maximal extracted value, is all about participants in the network trying to add, remove, change transactions that are included in a block to try and improve their value that they can get out of them. And so they'll front run or back run or arbitrage. So they'll see price discrepancies is arbitrage. Back running is when you can see a price movement in a transaction and you try and do something based on that to make a bit of money yourself. And front running is you can see that there's profit to be made by submitting the transaction that someone else wants to submit. So all these things aren't necessarily a bad thing. Like arbitrage is actually a good thing in that it helps to rebalance liquidity across chains, which is good for users and liquidity providers. So you can think that, say, you've got a coin which is worth, say, 92 on one chain and 90 on another. By arbitraging and supplying, so buying some of the coins on the chain where it was 90 and supplying them on the chain where it was 92, the price is going to tend to realign to 91 on both chains. Okay, so what do people do at the moment to try and prevent fraud proofs being front run? What they do is they have authorized watches. So you have some function to add a watcher, you become part of some approved watcher list, and as long as you're on that approved watcher list, you're all good. But this requires that one of these authorized watches is honest. And could all these watches collude? So if there was $1 billion at stake, could they collude? And so by restricting the set of watches, you're reducing the economic cost. And so if you didn't have it, you wouldn't even know who to bribe, because maybe there are 1,000 different watches. And as well, you can have lazy watches as well. So they only start watching once they can see a fraud proof is being submitted. And so they could just front run the honest watches, which is a bit of a problem. It's removing the incentivization, I guess, is the thing. So what could you do? Well, you can have a commit reveal scheme. And I even myself thought that this was a good idea and would work, but I've realized that that's not the case. So in a commit reveal scheme, you register with a commitment. So a commitment is the image that is the output of a hash function. And so you set up the pre-image to be something useful, like the proof. And then if you tie it to the message sender as well, then you're tying that proof to you and the commitment to you. And why this is good is that it means that someone can't just front run you, because that commitment is tied to your proof. And so, you can't just jump in. But, when you do that register function, any of the other watchers will, know that fraud's happening. And so they could then think, well, look, we know what the commitment is, and we know what message sender is. So they could try out all the possible values of proof that they think are likely, or they could just be looking now and say, is that the right thing that's being claimed? And so they could work out what that proof is, which is not good. And so, going back, all of these commit reveal schemes are going to add to the latency. And we said that we didn't want to have a lot of latency, but now suddenly we've got more latency, which is not good. It's also adding cost, which is not good. You could add a salt. So you could have a random value called a random salt that makes up part of the commitment. And so the thing that's good about this is that the other watchers, they can't just guess what the proof is easily, because they don't know what the random salt is. So they can't do a brute force, try out all the possible values to work it out, because they don't know what the random salt is, and it's a large number. So it makes it an impossibly large search space. Which is what I've just said there. So the other thing to think about is that a front-running bot could target the application, and so they could wait for the submit proof to be submitted, and then they could call this function here to front run the lot. So they could work out, they've got the proof, and so they then come up with a commitment, and they call register and then submit proof all in the one transaction. So they could still front run you. And as well, they don't need to have a specifically designed contract. They could use this multi-call style thing, where you have an array of contracts, an array of call data that you plan to call. And Yeah, so they could do that as well. But by the way, don't copy the code I've got here directly. There's quite a few gotchas in this simplistic multi-call. So I've been thinking about it, and a possible solution for all of this is having a timeout between register and submit proof. And I know we've said we want to do these as quick as possible, but having a timeout seems to be a bit of a solution. And so what you do is when you register, you say, well, this is when you've got to wait until before you're allowed to submit the proof. And once that has gone past, then you can submit your proof with your random salt and everything, and you should be good. And so why this is good is that the attackers can't do everything in one transaction because they won't be able to wait for the timeout, which is good. So is this okay? And what are your thoughts? Well, why is a proof needed? I think that's the thing to think about. So it's obviously someone has submitted a malicious value, but why would someone do that? And the main reason I think that you're going to find people submitting malicious values is software bugs and, say, network issues causing wrong values to be generated. So it's not going to necessarily be anything malicious. It's an honest issue. And in which case the watcher should be able to detect the situation and submit a fraud proof. And, if someone's got a buggy software that's gone wrong, they're not going to be in a position to be submitting a fraud proof at that point because they're going to be dealing with their software. And a tester could be acting maliciously to submit a fraudulent value. And so, you can imagine that maybe they've been taken over by an attacker or something, or they could be acting maliciously. And so if the attester could see the watcher submitting the fraud proof, and they could front run with the register and submit proof, and that because they know what the proof needs to be. So even with that timeout, they know what's going on. But if the attester is attacking their own system, it doesn't make sense because their operating system is going to make far more money than trying this fraud proof, and so it wouldn't make sense. Unless, of course, so some protocols allow anyone to be an attester. And so the attester could be an attacker. So if if you're not making sure in your protocol that the attesters are heavily invested in the system, then they could be an attacker. So so then it really comes down to them being like an attacker. So they could be powerfully owning an attester, or they could be a malicious attester who isn't bought into the protocol. And so, in this situation, again, the watchers can submit a fraud proof. And if the attacker sees the fraud proof being submitted, well, they could front run it because, they know what the fraud is. But then, the watcher, they could submit their proof via Mev Boost so the attacker doesn't see the fraud proof submission until it's included in a block, which, could be a good idea. And I'm hearing you say, just a sec, what is Mev Boost anyway? And so what is Mev Boost? So Mev Boost is the thing that's followed on from flashbots, and about 50-something%, maybe 60% of all transactions that are in Ethereum at the moment use Mev Boost to get into the network. So they don't use the public transaction pool for transaction submission. So in this scenario, you've got validators, also known as block proposers. And so they're essentially the miners that we've had in Ethereum 1. So they're Ethereum 2, they're called validators. And so they'll run the Mev Boost software. And they'll take transactions, obviously, from the public transaction pool. But they also take blocks of transactions that are given to them via relayers. And relayers are parties that work with block builders and validators to come up with a set of transactions for the block. And so a user could submit transactions to a searcher, a builder, or directly to the public transaction pool. So searchers have their own set of transactions in their own transaction pool, and they use the transaction pool that the builders have got. And so they use the transactions in that private-ish, so private where it's lots of people are seeing it, but it's not the public one, transaction pool. And so they'll be looking for MEV opportunities. And then the builder will look for the set of transactions provided by the block builder, or by the searcher, should I say, that is the most valuable to it. So it'll look and say, all right, well, that batch of transactions is most valuable, so I'll put it in the block and I'll put it up first. And then but then equally though, the user could try and make their transaction super valuable to the builder and to push it up at the front of the block. The builder then tries to create a block that is most valuable to the validator. And so it's all about trying to have it so that, say, the builder will say, maybe the searcher will have a transaction in their batch, which is directly paying the builder. And then the builder might be have a transaction in its overall block that is paying a whole heap of money to the validator or the Coinbase account to try and improve the value of its block. So as they're doing this, they're decreasing their profit though, because they're paying someone else. So that's how MEV Boost works. So you could try and put your transaction into MEV Boost. So the question to think about is the attacker who's doing all this, are they a searcher or are they in collaboration with the searcher on your block builder? And if they are doing that, and they're going to have to give up a whole heap of their earnings that they would have had to the block builder, which will then also be giving up a whole heap of their earnings to the validator. So the watcher, though, maybe it could use an ethical block builder that doesn't allow front running. So, so there are all sorts of different types of block builders out there. And so some of them might or appear to be ones where they say, we don't front run. And so we're ethical. And so the question, of course, comes is that, each of these block builders will have a block. And they are going to, if you've got your ethical block builder, it's, you're not going to be sure that that block's going to go in as the next block, because the next block might be some front runnable one that's got lots of front running in it. And so actually one thing I do remember I should have mentioned in this MEV slide. So the builder gives the relayer and it works with the validator, and it gives signed headers of the transaction. So the validator doesn't know all the transactions ahead of time, and they're relying on the relayer to match them up with the best block. So they don't know what those transactions are until they've committed to putting them into a block and publishing it. So if there are ethical block builders, then couldn't you just do this? Just a sec. We've just said there's an unfront runnable block builder. So, do we need all these salts and commit reveal and timeouts, all that complexity? Do we need it? And so I think you still probably do, because like any system, relying on one piece that's definitely gonna work might not be good. And so I think you wouldn't want to just rely on some ethical block builder to stop the front running. And I think having an extra layering in the system of a commit reveal system with a salt and a timeout should give you the best protection. So the proposed solution is, using commit reveal with salt with timeout. And this should protect you against generalized front-running bots. And if you're using those sealed bids with MEV Boost with an ethical block builder, then I think the probability of front running should be greatly reduced. So that's my thoughts on it. And so this is a talk by me, but as part of the channel, there's we've got the meetup. If you want to join the Slack workspace to have discussions about this, there, go for it. All of the code in this talk is actually in the Etheng group Solidity example. So those commit reveal contracts are in there. So thank you for watching. Have a great day. Bye-bye.